welcome back to the next episode of Standing on the Shoulder of Giants. In 1946, astrophysicist Lehman Spitzer published a research paper titled Astronomical Advantages of an Extraterrestrial Observatory. In it, he meticulously laid out the scientific arguments and engineering challenges of building, launching and operating a space telescope. Spitzer imagined an immense space telescope with a mirror as large as 50 feet across, placed in an orbit around the Earth using the cutting-edge rocketry technology of the era to profoundly change humanity's vision of the universe. It was a brilliant but incredibly audacious idea. The paper was published more than a decade before Sputnik became the first human-made object launched into space orbit. Still, the idea caught the imagination of fledgling space programs around the world, who saw the scientific potential of sending a telescope beyond the blur-causing nuisance of Earth's atmosphere. Almost half a century later, NASA would achieve the launch, repair and successful operation of a telescope similar to the one that Spitzer had conceived so many years prior, the Hubble Space Telescope. The initial ideas of placing telescopes in space could be tracked back to the early 20th century. In the 1920s, as rocketry was taking off, German engineer and physicist Hermann Oberth published work from his doctoral thesis mentioning that telescopes could be propelled into Earth orbit by the rockets he was working on. In the 1930s and 1940s, astronomers such as Henry Norris Russell fantasized about the epic possibilities that would be opened up to them by observatories built on the Moon. The appeal of telescopes in Earth orbit or on the Moon was clear and simple. It put our most valuable tools for astronomical research beyond the boundaries of Earth's atmosphere. When using a telescope here on Earth, the atmosphere basically causes nothing but problems, aside from allowing its observers to breathe. Turbulence in the atmosphere causes seeing, that same phenomenon that the modern deformable mirrors and adaptive optic systems work so hard to counter, which inevitably blurs the images captured by telescopes. Our observatories peer through the thicker swathes of the planet's atmosphere when focusing on objects in space that are close to the horizon. It becomes extremely difficult to capture clear images at all. Wouldn't it be better and make for easier, clearer astronomical observations to simply put the atmosphere behind us entirely and take the observations from space? A telescope in space would unarguably be better for the practice of astronomy, but the engineering challenges were immense. When Lehman Spitzer wrote his paper, no object had ever been launched into Earth orbit. During the following decade, a few astronomers took observations from space using detectors on board suborbital rockets, but the detectors were tiny and the rockets only spent a few minutes at the altitudes required to carry out their observations. Even as the space program was beginning, everyone understood that weight would be a major concern, since heavier objects required larger and more powerful rockets to carry them into orbit. Sputnik weighed less than 200 pounds when it was launched in its orbit in 1957. The Hubble Space Telescope ultimately weighed just over 12 tons when it was launched in 1990. And remember that the mirror for the 200-inch telescope at Palomar weighs 14.5 tons by itself. Even beyond weight, telescopes here on the ground were delicate and complex systems requiring support infrastructure, regular repair and maintenance, and most important of all, perfectly shaped mirrors. These facts made Spitzer's publication audacious, but not impossible. He was the first scientist to propose a concrete and carefully reasoned plan for putting telescopes in space. Combining the latest research on rocket technology and telescope building, he had grand plans for the potential of this space-based astronomy, imagining the possibilities of everything from a petite 10-inch telescope to an enormous 50-foot observatory. His proposals were largely met with mild skepticism within the astronomy community until Sputnik was launched into space, bringing Earth orbit satellites and all of their accompanying possibilities to the world stage. Even then, astronomers were still nervous about throwing support behind a space-based telescope. At the time, the 200-inch telescope was working wonderfully, and it had been built for a tenth of the estimated $100 million cost to launch a single, simple space satellite. Astronomers also worried about pouring years of time and effort into a telescope that would simply explode on a launch pad, destroying an immense investment by the field. Still, telescopes were a part of early space program efforts. By 1968, NASA had launched several small space telescopes, including the Orbiting Astronomical Observatory, or OAO, a collection of small telescopes that observed ultraviolet light, a wavelength impossible to capture from beneath Earth's atmosphere because most of it is absorbed by the ozone layer. The OAO relayed data for 4 years, quadruple its expected lifetime, and conclusively demonstrating that space-based telescopes was a successful and worthwhile endeavour. Fresh off these early successes in 1968, NASA began planning for a space-based telescope with a 10-foot mirror, creatively nicknamed the Large Space Telescope, or LST, with a planned launch date of 1979. However, the LST quickly ran into setbacks. Public interest in space exploration waned following the 1969 moon landing and the conclusion of the Apollo space program in 1975. Moreover, building a telescope to operate in space was far more costly than building one here on Earth, and with the public questioning more spending on space programs, the United States Congress grew critical of the project. Spending cuts in 1974 eventually led to Congress removing all funding for the telescope project, and Spitzer's dream of a powerful space telescope appeared to be in jeopardy. In the end, the support and success of NASA's space astronomy program and the ultimate funding, creation and launch of the Hubble Space Telescope can be credited to NASA's first chief of astronomy, Nancy Roman. Nancy Roman was born in Tennessee in 1925. Her interest in astronomy began as a young girl when she founded a small astronomy group with other girls at her school at the age of 11. She went on to study astronomy at Swarthmore College and then the University of Chicago. Roman was a successful researcher and skilled observer, studying the classification and spectra of the stars in the auspicious tradition of the Harvard computers. However, she was aware as her career began that there were very limited career options available to women, with few female tenure track or tenured professors working in astronomy. Roman was working at the Naval Research Laboratory in Washington, D.C. when Sputnik was launched in 1957. Less than a year later, the National Aeronautics and Space Administration, NASA, was officially formed, and a few months after that a colleague asked her, seemingly offhand, whether she knew of anyone who might be interested in coming to NASA to set up a brand new program in space astronomy. Roman did in fact know someone who was interested, and she started her new job as NASA's first chief astronomer in 1959. She was tasked with overseeing the promotion, design and success of the world's first space telescopes. Roman became a tireless champion of space astronomy, drumming up support from the astronomy community, the public and Congress to support what would most certainly be an expensive undertaking. Based on early proposals from the scientific community, Roman oversaw the launch of the orbiting astronomical observatories. Their eventual success lent some strong support to NASA's hopes of building a large space telescope. By 1971, Nancy Roman had led the creation of the Large Space Telescope Science Steering Group, which set to work on actually designing a space telescope. Another burgeoning NASA project at the time, the Space Shuttle, factored heavily into their plans, leading to an imagined telescope that could fit into the cargo bay of the shuttle to be carried into orbit and then serviced regularly by the visiting astronauts. Congress temporarily cut funding for the telescope in its 1975 budget, but this immediately sparked fervent efforts to restore the funding by Nancy Roman, telescope project scientist Bob Odell, and the growing number of astronomers pinning their hopes on their project, including Lehman Spitzer. Finally, in 1977, Congress approved funding for the LST, and the project officially began. The first steps, beginning the painstaking grinding and shaping of the telescope's crucial 7.9-foot primary mirror, and training astronauts in a massive underwater facility to simulate the weightlessness of space for future missions to the telescope. 2 years later, Roman retired from NASA, having spearheaded the creation of NASA's space astronomy program and the development of a large space telescope. Launch was scheduled for 1983, and astronomers hoped to be taking breathtaking new pictures of the universe soon afterward. By 1983, the LST had been officially renamed the Hubble Space Telescope, but it still wasn't in space. The grinding and polishing of the primary mirror had been delayed until 1981, and the telescope's full optical assembly hadn't been completed until 1984. The continued delay pushed Hubble's launch back to September of 1986. Then on January 28th of 1986, the Space Shuttle Challenger broke apart 73 seconds after its launch from Kennedy Space Center in Florida, killing all 7 crew members and bringing NASA's shuttle program to a halt for over 2 years while the accident was investigated. The telescope had been in the final stages of being prepared for launch, and was kept in a clean room, powered up and pumped full of nitrogen to displace any nominal air or prevent water vapor from condensing on telescope parts that could later ice up in orbit. During the day, work on the telescope continued, testing different telescope components and continuing to prepare Hubble's ground software, which would be used to control the telescope in orbit from the Space Telescope Science Institute headquarters in Baltimore, Maryland. Crewed space shuttle flights resumed in 1988. The Hubble was finally launched by the Space Shuttle Discovery on April 24th of 1990. After startup and initial testing, the official first light image from Hubble was captured on May 20th, with the telescope trained on a nearby stellar cluster. Almost immediately, astronomers including Roger Linz, Chris Burrows and Sandy Faber noticed a problem in the first images from the telescope, most notably a circular halo of light surrounding the brightest star in the cluster. The Hubble mirror, as the world would eventually learn, had been launched with a severe flaw. It was suffering from an optical phenomenon known as spherical aberration. If a mirror is shaped like a segment of a perfect sphere, it will focus light at different points along its optical axis depending on where that light hits the mirror. Light bouncing off the mirror close to the center will focus to a point further away from the surface, while light hitting the edges of the mirror will focus to a different point closer to the mirror's surface. Since an eye or camera can only be placed at a single point along the optical axis, this results in an image that looks layered or blurry, with part of it in focus and part of it spread out to make a larger or smaller unfocused image. For a round star, this would produce a distinctive blurred halo seen in the first image. Spherical aberration is easily avoided by shaping and grinding mirrors to a parabolic rather than a spherical shape, a technique that telescope builders like George Hale of California and Roger Angel of the Arizona Mirror Lab understood well. However, the parabolic shape must be perfect. Remember, a mirror's shape must be formed to within 5% of the wavelength of light that it is focusing. For a telescope like Hubble, the margin of error was mere nanometers, an impressive number, but a precision that should have been easily achievable with modern-day facilities. Astronomers and engineers were eventually able to take Hubble's ugly early images and back-solve the problem, calculating that the mirror's edge had been ground too flat by an appalling 2000 nanometers, which introduced the flaw of spherical aberration. The difference between error and perfection may have been tiny by most standards, smaller than the width of a human hair, but it didn't matter. It had rendered the Hubble mirror seemingly unusable. For a time, the astronomers and team members thought they were doomed, left with a bus-sized piece of space junk orbiting Earth. Eventually, a team comprised of some of the world's best astronomers and telescope builders, including Lyman Spitzer, Sandy Faber, and Roger Angel, the Arizona mirror maker, convened to come up with a solution. In the end, a complicated new instrument was designed for Hubble, known as COSTAR, the Corrective Optics Space Telescope Axial Replacement, which was painstakingly designed to reflect light from Hubble's own mirrors to 3 of the cutting-edge scientific instruments that had been launched with Hubble to record its first observations. A 4th instrument would be sacrificed to make room for COSTAR's installation. By designing COSTAR with a series of mirrors shaped specifically to correct Hubble's vision problems, they hoped they would be able to overcome the mirror error and finally start taking perfect, sharp images. After several years of building the new instrument, the Space Shuttle Endeavour launched in December 1993 with a daunting task: grab the Space Hubble telescope, tuck it into the shuttle's cargo bay, and then make a grueling series of 5 lengthy spacewalks to install COSTAR and make other small repairs. The fix worked. When Hubble took its new second light images in December of 1993, the image came back sharp and clear. The space telescope was finally up and running. The mistake with the mirror was eventually traced back to an instrument called a null corrector, designed to check that the mirror was being ground properly. One lens in the null corrector's optics had been installed incorrectly, 1.3 mm out of position, leading to the eventual grinding error. Engineers had actually prudently tested the mirror multiple times, including once with an older instrument. The test with the older instrument came back reporting spherical aberration, but the fancy new null corrector was assumed to be much more reliable than their old equipment, and they dismissed the test results as bad data. COSTAR continued to work as a corrective optics instrument for nearly 16 years until it was removed during Hubble's 4th and final servicing mission in 2009. By then, other servicing missions had removed Hubble's old instruments and replaced them with new ones, and each new instrument contained its own personal set of corrective optics to account for the mirror's problems. Since 1993, Hubble was fully operational as the world's first large optical space telescope, realizing the dream that Lyman Spitzer had first published in 1946 and that Nancy Roman worked on tirelessly to make a reality. An immense team of astronomers, engineers and astronauts helped bring Hubble into the world, and the staff of the Space Telescope Science Institute in Baltimore still keep Hubble running today. It celebrated the 30th anniversary of its launch in April of 2020. Hubble has made groundbreaking discoveries across every single subfield of astronomy. One early but memorable image came in 1995 when astronomers decided to point Hubble at absolutely nothing. The observation had been Bob Williams's idea. Williams was the director of the Space Telescope Science Institute, and as part of that position he was granted 10% of the available telescope time on the Hubble. Normal Hubble time was doled out in orbits and fiercely competitive, with astronomers submitting lengthy scientific proposals for peer review and a 1 in 6 chance of being granted telescope access. However, the 10% of time granted to Williams, known as Director's Discretionary Time, could be used for whatever he chose. Still, the choice to stare at nothing seemed odd at first, especially coming just 2 years after Hubble's crucial repair, when the telescope was still trying to make up for lost time. Williams explained his reasoning to his colleagues. Pointing Hubble at an empty patch of sky for a long time, more than 100 hours in total, would make for an unprecedented long and deep exposure, opening the eye of the most sensitive telescope in the world in the hopes that they might capture the light from some of the faintest faraway galaxies ever seen. The results were astounding. The little empty patch sky Williams had chosen near the handle of the Big Dipper was in fact teeming with thousands of faint galaxies. Some of the galaxies were 12 billion light-years away. The light Hubble had captured had been emitted by galaxies less than 2 billion years after the Big Bang, and had spent the intervening 12 billion years sprinting across the universe before ultimately landing on Hubble's mirror. The observation became known as Hubble Deep Field, and the experiment was repeated in 2004 and again in 2012, producing the Ultra Deep Field and the Extreme Deep Field. The Extreme Deep Field captured more than 5,000 galaxies. The most distant were 13.2 billion light-years away, showing us light emitted just 500 million years after the Big Bang. Hubble also made a number of impressive discoveries closer to home. In 1994 it took some of the first images of the impact when comet Schumacher-Levy 9 crashed into Jupiter. In 2005 it discovered Nix and Hydra, the two tiny moons orbiting the dwarf planet Pluto, and in 2016 it captured what seemed to be enormous plumes of water erupting from the surface of Europa, one of Jupiter's moons. Hubble's surveys of nearby galaxies are so sharp that astronomers are able to resolve individual stars within the galaxy. These images have proven to be extremely valuable, even in the many years since Hubble first captured them. Telescopes on the ground now regularly discover supernovae, the bright flashes from explosive stellar deaths, and pinpoint their location in distant galaxies. By comparing the locations of these supernovae to pre-explosion pictures of the same galaxy taken by Hubble, astronomers can now identify the stars at the explosion site. Follow-up images taken with Hubble after the light from the supernova fades will sometimes reveal that a star has disappeared, allowing astronomers to identify the exact star that had died and produced the supernova. From these observations we've been able to gather invaluable data about the final stages before a star's death for the very first time. At larger distances, the Hubble Space Telescope is appropriately used today by multiple teams trying to measure the Hubble constant, a single number that's used to quantify the expansion of the universe. As we've seen in earlier programs, teams use observations of distant Cepheid variables or cleanly resolved images of stellar clusters in other galaxies to calculate distances and refine the current accepted value of this elusive constant. Hubble has also studied the supermassive black holes at the center of galaxies. mapped the distribution of dark matter and revealed that the universe likely contains 10 times the number of galaxies we had previously believed existed. Hubble has also produced some of the best images ever captured of nearby stars and nebulae. Hubble's cameras have captured unforgettable pictures of objects like the Helix Nebula, the leftover gas puffed off from a star like our Sun at the end of its life, the Crab Nebula, the explosive remnant of a supernova, and perhaps Hubble's most iconic photograph, the Pillars of Creation, an area within a nebula where new stars are born. Hubble images now show up everywhere, from the front page of the New York Times to the backgrounds of our smartphones. Like Edwin Hubble himself, many of the researchers that use the Hubble Space Telescope study the universe using visible light, the same light that our eyes rely upon for us to see. The power of optical space telescopes may be impressive, but it's only one window into the vast wealth of light that space has to offer. In the next program we'll explore another realm of the electromagnetic spectrum that gives us totally new and scientifically powerful view of the universe: radio light.